chapter is carboxylic acid derivatives. This is carboxylic acid RCOOH. When we replace the OH group of carboxylic acid with some other group, it can be chlorine group, it can be OCOR, OR- or NH2, then this is called carboxylic acid derivative. The general formula of carboxylic acid derivative is RCOZ, where Z is the group with which we have replaced the hydroxyl group. This is acid chloride, acid anhydride, ester, acid amide. The structure is RC double bond O of carbonyl group, and this is Z, that is the group. Now here, this double bond is represented by black lines here. Why we have shown a double bond with carbon and the Z group? Because due to resonance, Z group also attains a partial double bond with carbon. That's why we have also shown it in the black lines. Next we have nucleophilic acyl substitution. All acid derivatives, that is RCOZ, in nucleophilic substitution reactions, they all participate in nucleophilic substitution reactions in which chlorine, OOCR, NH2, OR-, these all are Z groups. They are replaced by some other nucleophilic substituent, Nu negative. So this is the derivative. When we reacted with a nucleophile, this nucleophile attacks on this derivative and it replaces the Z group, and Z negative we attain here. Now let us look at the mechanism of nucleophilic acyl substitution. It involves two steps. The first step is addition and the second step is elimination. In the first step, this carbon is sp2 hybridized and this is Z group, this is double bond O. The nucleophile attacks on this carbon and this double bond shifts to oxygen. This is a reversible step. Now the geometry, the hybridization becomes sp3 of the carbon. This is tetrahedral intermediate because it forms a tetrahedral geometry. Here, the oxygen has attained a negative charge because the bond was shifted to oxygen, and the nucleophile gets attached to the carbon, and here is the Z group. In the step 2, that is elimination, this step involves the leaving nature of this Z group. When this lone pair shifts to the oxygen carbon bond, it becomes a double bond again, and this bond gives its electrons to the Z group, and the Z group leaves the carbon atom. This Z group acts as a good leaving group. The weaker the base, the better it would be a leaving group. So the Z group must be a weak base for being a best leaving group. The order of ease of leaving group is in this way. Chlorine is a very weak base and hence it is the best leaving group, and followed by RCOO negative, R-O negative, and NH2 negative. NH2 negative is the strongest base. These both are strong bases and hence they both are not better leaving groups, they are weak leaving groups. Now let us summarize the mechanism again. Here, nucleophile attacks on the carbon and double bond shifts to oxygen. This is the acyl compound. In this step addition occurs and this is a reversible step. Then the lone pair of oxygen shifts to carbon-oxygen bond and Z group leaves its position, and this is an anionic intermediate. This step involves elimination, so here we get a substitution product, RCONU, and this is Z negative, the leaving group. Then we have the relative stability of acid derivatives and the order of reactivity. This is an important topic and is usually asked in exams, so I may prefer you to write it along with me. In the first step, this double bond shifts to oxygen. Oxygen gets a negative charge and carbon a positive charge. Then the lone pair of Z group, it shifts its lone pair to this ZC bond. So Z gets a positive charge and here a double bond is obtained and oxygen is negative. The third step, the third structure, is the most important structure, because on the basis of this we'll get to know all the things further. Now, resonance form 3, this is the resonance form 3, strengthens the bond strength between Z and carbonyl carbon. This strengthens the bond strength between this carbon and this Z group, because it attains a double bond through double bond character and involves dispersal of positive charge on carbonyl carbon, because positive charge is gained by Z group now. So this bond is very stable. Double bond is more stable than single bond, and hence the strength between Z and C is strengthened. Greater the contribution of structure 3, greater would be the stability of acid derivative. Right? It's clear? Now, we know that X, that means halogens, are most electronegative, followed by oxygen and nitrogen. Nitrogen is least electronegative. Now, this structure, look at this structure. We have drawn 4 structures, in which first Z group is chlorine, second Z group is OCOR, third Z group is OR-, and fourth Z group is NH2. Now, one more thing I want to tell you. We have to learn 4 of these in the same order I have written here. Acid chloride, acid anhydride, ester, acid amide. I will tell you why we have learned these structures in this form only. Now, poor sidewise overlapping between 3p orbitals and 2p orbitals. 3p orbitals of chlorine and 2p orbitals of this carbon. Due to different orbitals, it have a poor overlapping due to large difference in their sizes. So double bond between chlorine and carbon is not easily formed, this chlorine and this carbon. So this is the weakest among stability order. Next we have OCOR. Oxygen is more electronegative than nitrogen and cannot accommodate positive charge easily. Right? Esters are more stable than anhydrides. Why esters are more stable than anhydrides? This is anhydride and this is an ester. Let us see. Because both of the carbons are bonded to oxygen. Here this oxygen is attached to C double bond O group, carbonyl group, and this oxygen is attached to R- group. In esters, R- group is electron withdrawing group. So due to plus I effect, this structure is more stable than this structure, because in anhydrides, C double bond O is electron withdrawing group, and hence it withdraws electrons from oxygen, so destabilizing the structure due to minus I effect. So that's why esters are more stable than anhydrides, followed by chlorides. Now let us come to nitrogen. Nitrogen is relatively less electronegative. As it is less electronegative, it can accommodate more positive charge, and hence it is more stable. It is in fact most stable among 4 of these, because it attains positive charge, and hence this structure is more stable. So the order of relative stabilities is amides, then esters, then acid anhydrides, and then acid chlorides. That's why I've told you to learn these structures in the same order, because this was the first, second, third, fourth, and we can easily mark them according to their relative stabilities in the same order. Now we have order of reactivity of acid derivatives towards nucleophilic acyl substitution. You can see that the order of reactivity is just the reverse of order of relative stability. Here chlorine is more stable than anhydrides, then esters, and then amides. Now first is electron deficiency on acyl carbon. More the electron deficiency on acyl carbon, this is acyl carbon of acid derivative, better the site for nucleophilic attack. Chlorine, oxygen, nitrogen directly attached to acyl carbon exert an electron withdrawing effect. These all are electron withdrawing groups, so they exert an electron withdrawing inductive effect on acyl carbon. This decreases electron density of the carbon, this carbon. But at the same time, all these atoms have unshared pairs of electrons also, which undergo resonance interaction with acyl carbon, thus increasing electron density at it. Also, these groups, chlorine, oxygen and nitrogen, they have electron pairs on them, so they donate the electrons to carbon and hence make it more electron rich. Also, we have read in the first point, more the electron deficiency on acyl carbon of acid derivative, better the site of nucleophilic attack. But due to resonance, these all atoms donate its electrons to a carbon, but due to inductive effect, they withdraw also. So the conclusion is, this effect increases as we go from chlorine to OOCr, OR- to NH2. So it is more prominent in this structure and least prominent in this structure, and hence this is more reactive, in fact the most reactive structure among four of this, and this is the least reactive. The net result is carbon on acid chlorides has minimum electron density and it goes on increasing as we move to anhydrides, esters and amides. Hence the reactivity order is as above. Role of acid catalysis in nucleophilic acyl substitution. H plus ion gets attached to carbonyl oxygen, and hence oxygen can now acquire pi electrons of C double bond O more easily, and hence carbonyl carbon becomes even more susceptible to nucleophilic attack. This H plus attacks to this oxygen and becomes OH positive. This nucleophile now can easily attack to this carbon, and hence we obtain this structure easily. Next we have acidic and alkaline hydrolysis of acid derivatives. The mechanism of acidic hydrolysis. First H plus attacks on oxygen, the oxygen gets protonated, then this water, because we are doing hydrolysis, so this water, oxygen attacks to this carbon and this bond is shifted to oxygen. Now in the next step, from here, this is OHH, water is attached to a carbon. This bond shifts to this bond, OC bond, and Z leaves the position. So we get R C double bond OH, that is carboxylic acid plus HZ, the group with hydrogen and H plus ion. The mechanism of alkaline hydrolysis is OH negative. Instead of H plus, OH negative attacks on the carbon and this double bond shifts to oxygen. Oxygen gets negative charge. Then this lone pair shifts to this bond and Z group leaves its position. Then again carboxylic acid is formed plus Z negative. Then again OH negative attacks on this and we get RCOO negative plus water. From here H plus and OH negative combines to form water. Now we have interconversion of acid derivatives by nucleophilic acyl substitution. Due to the difference in the reactivity of acid derivatives towards nucleophile substitution, it is usually possible to convert a more reactive acid derivative into a less reactive, but not vice versa. Here, acid chlorides, we have learned they are most reactive, so they can be converted to anhydrides, esters and amides. But we cannot convert any of these to form chlorides. Again, anhydrides are lesser reactive than chlorides, so they cannot form chlorides, but they can form esters and amides. Esters can form amides only, but not anhydrides and chlorides. So we can go in this way, but not the reverse. Now the first acid derivative is acid chloride, RCOCl. Here OH is replaced by chlorine. Nomenclature is done When we have any acid, for example methanoic acid, we have to just cut ic acid and replace it by aryl chloride. For example, methanoic acid, it becomes methanoyl chloride. Benzoic acid, benzoyl chloride. And two more examples. Preparation of acid chlorides. First is from carboxylic acid. Let us take acetic acid, and we have reacted with thionyl chloride, SOCl2. It forms acetyl chloride, CH3 C double bond O Cl plus SO2 plus HCl. In aromatic form, we have taken benzoic acid, we have reacted it with PCl5, it forms benzoyl chloride, POCl3 plus HCl. Second method is from carboxylic acid salts. We have taken sodium, salt of acetic acid. We have reacted with PCl3. It forms acetyl chloride, again this one, plus Na3PO3. Calcium propionate with sulfuryl chloride. It forms propionyl chloride plus calcium sulfate. Sodium benzoate reacted with POCl3 forms benzoyl chloride plus NaCl plus NaPO3. Now we have physical properties. Physical state, first of all. They are colorless hygroscopic liquids. They have low melting solids, irritating odor, fume in moist air due to formation of HCl by their hydrolysis. Solubility. They are soluble in organic solvents because like dissolves like. Boiling points. Chlorides have no acidic hydrogen. Hence, they do not form hydrogen bonds because acid chlorides do not have any acidic hydrogen. Therefore, low boiling point than their parent acid from which they are formed. Now we have chemical properties. Firstly, the reactions with nucleophiles. In this, conversion into acids and other acid derivatives takes place. First is hydrolysis. When acyl chloride, or we can say acid chloride, one and the same thing, it is reacted with water, HOH, or we can say H2O. From there, HCl is removed and we get carboxylic acid. Reaction with alcohols. This is called alcoholysis. R C double bond O Cl. This is acyl chloride or acid chloride. It is reacted with alcohol because it is alcoholysis. HCl is removed again. We form ester and HCl. For example, Schotten-Baumann reaction is also this type of reaction. Third is reaction with ammonia and amines. Ammonolysis with ammonia and aminolysis with amines. Acid chloride reacted with ammonia forms RC double bond O NH2. This is amide plus ammonium chloride. When reacted with amine, they form RC double bond O NHR dash. Only just a difference of R dash group plus this byproduct. Reaction with carboxylic acids on or their salts. This is carboxylic acid. We have reacted with acid chloride in the presence of pyridine. We also usually write pyridine as PY. I will use it further. So we get RCOO CR dash. Okay, this seems to be quite complicated, but it's not anything but just anhydride, right? R dash plus pyridine hydrochloride. Other reactions of acid chlorides are reduction. Firstly, when acid chlorides are reduced in the presence of lithium aluminium hydride and acidic hydrolysis is done, we get primary alcohols. This is also a very important reaction. Then we have Rosenmann's reaction. Benzoyl chloride is treated with hydrogen in the presence of Lindlar's catalyst, that is PdBaSO4. This is lead barium sulfate in the presence of hydrogen. It forms benzaldehyde. Thus chlorine is replaced by hydrogen and benzoyl chloride becomes benzaldehyde plus HCl. We can easily get to know from this that HCl is removed from here and this H gets attached to this carbon here. Next reaction is reaction with organometallic compounds. For example, R-CD, R dash. That means dialkyl cadmium, we can write it as R dash. Cadmium valency is 2, so 2 alkyl groups will be attached. From here we have taken 2 acid chlorides, C double bond O Cl, or C double bond O Cl. From here we remove 2 chlorines and 1 cadmium. Can you see the reaction? Cadmium chloride is removed and the rest which is left are C double bond O R dash or C double bond O R dash. 2 molecules of ketone is formed. Very easy reaction, not complicated at all. Then we have Friedel-Crafts acylation. Any aromatic compound treated with acid chloride in the presence of anhydride aluminum chloride forms ketone plus HCl. Then we have hydrogenation of alkyl group. When this is in this we have shown alpha hydrogen because it is important in this reaction. Alpha hydrogens are the main priority. I mean, they are required in this reaction. Otherwise this reaction cannot be formed, cannot be done. In the presence of chlorine and phosphorus, alpha hydrogen is replaced by chlorine. So that was all about alpha hydrogens. If there is no alpha hydrogen, this reaction will not take place at all, plus HCl. Then we have aromatic substitution. This group, this is acid chloride group, is a deactivating group. Therefore, substitution occurs on meta position. So that was all about acid chlorides. Then we have acid anhydrides. This is the structure of anhydride. Nomenclature is done by replacing acid by anhydride, like ethanoic acid to ethanoic anhydride. Then we have preparation. Acetyl chloride. We are preparing it from chlorides first, acid chlorides. We have reacted with acetic acid. From here HCl is removed in the presence of pyridine. This is pyridine, I have already told you that we may write it as PY also. And we get anhydride plus pyridine hydrochloride. You can see CH3 C double bond O. From here O C double bond O CH3. This forms anhydride. Next we get 2 molecules of carboxylic acid, that is acetic acid. From here water is removed in the presence of P2O5. We heat it, dehydration takes place and we get an anhydride. Next we have a ketene. Ketene, it's not ketone. We have a double bond here, so we name it as ketene. Reacted with carboxylic acid to form anhydride. Next comes the physical properties. First is the physical state. Anhydrides of lower aliphatic acids are colorless, sharp-smelling liquids, while aromatic anhydrides are colorless solids. Boiling points: higher boiling point than corresponding acids. This is because there is no hydrogen bonding, but size is very large. So due to this, there are large van der Waals forces between the molecules and hence more boiling point. Then we have solubility. Lower members somewhat are soluble in water, but higher members are only soluble in organic solvents because of the principle of like dissolves like. Then we have chemical properties. First is hydrolysis. When anhydride is treated with water, it just forms carboxylic acid simply. Alcoholysis, when treated with alcohol, let us say ethanol, it takes out H plus from here and CH3COO negative from here to form acid plus CH3COO, CH3CO, C2H5. This is another ester formed. This is an ester, CH3COO, C2H5. Then we have ammonolysis. When it is treated with ammonia, it forms etamide and ammonium acetate. Friedel-Crafts acylation. Aromatic compound when treated with acid and anhydride, it forms ketone plus carboxylic acid. Reduction, when it is reduced with lithium aluminum hydride and acidic hydrolysis is done, then we get benzoyl alcohol. The next topic is esters. The general formula is R C double bond O O R dash. This is when we replace OH by OR dash. The nomenclature is done by rejecting ic acid and replacing it by ate. For example, this is ethyl ethanoate 8. Right? The preparation is done. First method, acetic acid is treated with benzyl alcohol. This is benzyl alcohol in the presence of any acid H plus to form benzyl acetate. This is an ester plus water. This reaction is called esterification reaction, and this is an important reaction. The mechanism of esterification reaction, here this is acid, carboxylic acid, it is treated with H plus, thus attacks on oxygen to form OH positive, it protonates the oxygen, and then this bond, double bond shifts to OH bond, and this oxygen, the lone pair on oxygen, is attacking on this carbon. So this is the structure formed, and this positive charge is attained by the oxygen, this one. Now this OH bond shifts to oxygen and a base is attached to the hydrogen. So here we get O, CH2, CH3 as it is, and when it is attacked by H positive, this lone pair shifts to H plus and it forms a bond with oxygen. Here OH positive. Now this lone pair shifts to OC bond and this bond is moved away, and we form a structure like this. Here water attacks again on hydrogen, and this is removed from here and we get ester plus H3O positive. Second is reaction between acid chloride or acid anhydride and alcohol. This is acid chloride, it is reacted with alcohol to form ester plus HCl. Anhydride is reacted with alcohol to form ester plus acid. Third is reaction of carboxylic acid with diazomethane. This is benzoic acid reacted with diazomethane. It forms methyl benzoate plus nitrogen. Physical properties, physical state firstly, they are colorless, they have pleasant smell, and they are liquids or they may be solids. Solubility, they are generally insoluble in water, but they are soluble in most of the organic solvents because like dissolves like. Boiling points, due to lack of hydrogen bonding, esters have low boiling point. Then we have chemical properties. First is hydrolysis. When esters are treated with water in acidic medium, they form RCOOH plus R-OH alcohol. But when they are treated in the basic medium, they form RCOO negative plus R-OH alcohol. The mechanism of alkaline hydrolysis first. In alkaline hydrolysis, OH negative group attacks on carbon and this bond shifts to oxygen. Now this lone pair shifts to oxygen carbon bond and this bond shifts to oxygen, and here we get carboxylic acid. Now this OR dash, which have been removed from here, this attacks on this hydrogen and this bond shifts to oxygen and we get this structure plus R-OH. This is resonance structure. The evidence to support the mechanism is kinetic studies. Second order kinetics, because it depend on concentration of ester and OH, two reactants, so second order kinetics. Second, isotopic labeling experiment. This oxygen is named as oxygen 18 isotope. This reacts with OH negative, it forms CH3COO negative, and this oxygen comes with the alcohol. So it is clear from this isotope labeling experiment the mechanism of alkaline hydrolysis is this. Then we have stoichiometric studies. Acyl cleavage is also supported by stoichiometrical studies of alkaline hydrolysis of optically active esters. Acidic hydrolysis, H plus attacks on oxygen. Here oxygen gets protonated, then water attacks on carbon, this bond shifts to oxygen. This structure is formed. Then hydride shift, H plus shift takes place, and we get here ORH positive. Now alcohol is removed from here, and this bond shifts to carbon, and H plus is removed here, so we get a carboxylic acid. Evidence in favor of mechanism. In acid catalyzed hydrolysis, acid is required in very small amount because it acts as a catalyst only, while in base or alkaline hydrolysis, base is required in equimolar amounts because it is one of the reactants and not a catalyst only, right? Acid catalyzed hydrolysis is reversible as seen from the mechanism, while alkaline hydrolysis is irreversible. So these 2 points may be also written in the differences between the two. Ammonolysis, esters are reacted with ammonia to form amide plus alcohol. Next reaction is alcoholysis or transesterification. In this reaction, ester is treated with alcohol in the presence of H plus or RHO negative. And here R groups replace each other. Here R dash becomes R double dash and R double dash becomes R dash of alcohol and ester. Then we have reduction, catalytic hydrogenation. This is ester in the presence of hydrogen and copper chromate at 525 Kelvin and 200 to 300 atmosphere pressure. It forms alcohol and alcohol. This is a different alcohol and this is a different alcohol, right? Then we have chemical reduction. This method is named as Bouvelt-Blanc method. Here methyl laurate in the presence of sodium and ethanol forms lauryl alcohol plus CH3OH, the other small alcohol. Then we have reaction with Grignard reagent. Here this is ester, it reacts with Grignard reagent. Here a step is quite different. Just look at this step. The ester, this oxygen of ester is removed and this R dash group is replaced by this R dash, double dash. And this OR dash group goes to magnesium. OR dash attacks to magnesium here. Now again Grignard reagent is added and this Grignard reagent attacks on carbon and oxygen to form this. Now hydrolysis is done in the acidic medium and we get 3 degree alcohol plus MgXOH. Then we have reaction with hydroxylamine. This is the ester reacted with hydroxylamine to form hydroxamic acid plus alcohol. Then we have Claisen condensation. In Claisen condensation, ethyl acetate, which is having an alpha hydrogen, is treated with sodium ethoxide. From here, 2 molecules of ethanol is removed and we get, on acidic medium, we get acetoacetic ester. So next we have acid amides. The last topic is amides. This is primary amide where no R group is attached to nitrogen, secondary where 1 group is attached, and tertiary where 2 groups are attached. Then we have nomenclature of acid amides. Here oic acid is replaced by amide simply. Here this is ethanamide. Now preparation, ammonolysis of acid derivatives. This is acid chloride reacted with ammonia to form acid amide because chlorine is replaced by NH2 group and ammonium chloride is a byproduct. Thermal decomposition of ammonium salts. When we heat ammonium salts, they form amides plus water. Partial hydrolysis of nitriles in the concentrated HCl, when hydrolysis is done, it forms acetamide. Next we have physical properties. Physical state. Formaldehyde is liquid. Other amides are colorless crystalline solids at room temperature. Solubility. Members up to 6th carbon are soluble in water because of formation of hydrogen bonding. Boiling point. Strong intermolecular hydrogen bonding. Amides have high boiling point because they have intermolecular hydrogen bonding. Then we have chemical properties. They are amphoteric in nature. This is shown by these reactions. This is amide. It reacts with HCl to form a salt. We can say amide hydrochloride. So it is clear that it is a base. And when amide reacts with HgO, it is a base. It forms mercuric salt plus water. So this is an acid. From these two reactions, it is clear that amide behaves as a base and an acid. So it is amphoteric in nature. Then we have hydrolysis. Its hydrolysis in acidic medium yields RCOOH plus ammonium ion, and in basic medium it forms RCOO negative plus ammonia. Dehydration. 3 molecules of amide reacts with P2O5 to form nitrile plus H3PO4. Reaction with nitrous acid. When it is treated with NaNO2 plus HCl, they both combine to form nitrous acid. When it is heated, it forms RCOOH, carboxylic acid, plus nitrogen plus water plus HCl, NaCl. Hofmann degradation. When amide is treated with bromine in the presence of KOH, it forms amine plus K2CO3 plus KBr plus water. Then we have reduction. This is acetamide. It forms ethyl amine on reduction. So that was all about the chapter carboxylic acid derivatives. Thank you.